Hello friends, welcome back to my YouTube channel. This is seventh part of my discussion on mass transfer coefficients, and today I will be discussing how to find mass transfer coefficients in laminar flow. In part number 6, that is in the previous video lecture, I had derived the continuity equation, and I need that continuity equation in today's discussion. So let us begin the discussion. Okay, so let us begin by asking these questions to ourselves. Do we need mass transfer coefficients in laminar flow? We know in laminar flow mass transfer occurs only by molecular diffusion, and as far as molecular diffusion is concerned, we have equations that can be used for calculating mass transfer rates. Equations for calculating mass transfer rates, they are available. So therefore, in principle, we don't need mass transfer coefficients. Mass transfer coefficients are not required for laminar flow. But then why are we discussing them for laminar flow? The reason is it is desirable to have a uniform method to deal with both laminar and turbulent flow. In order to have a uniform method for dealing with laminar and turbulent flow, we are discussing mass transfer coefficients for laminar flow in this video lecture. We know that for turbulent flow, mass transfer rates are described in terms of mass transfer coefficients. So therefore, it is desirable, since it is desirable to have a uniform method to deal with both laminar and turbulent flow, we are having today's discussion. We are going to know how you can get mass transfer, or how you can calculate mass transfer coefficients in laminar flow. And the general technique that is used, for finding mass transfer coefficients in laminar flow, it is demonstrated, and for demonstrating that we are going to consider a relatively simple example. The technique used to find mass transfer coefficients in laminar flow, it is demonstrated by considering a relatively simple example. Let us move on. Now let us consider a simple example, as I said earlier. So the scenario in this case is a liquid is falling in a thin film in laminar flow down a vertical surface. So there is a vertical surface, and along this vertical surface a liquid is falling as a thin film in laminar flow. You have a liquid that is falling in a thin film, that too in laminar flow, down a vertical surface. So you have the vertical surface and the liquid is falling down in a thin film under laminar conditions. Now the liquid in this case, it is exposed to gas E, which then dissolves in the liquid. So the liquid, it is exposed to gas E. This is gas E, and the gas is getting dissolved into the liquid. So for our discussion, we are going to consider this as the Z direction and this as the Y direction. So from this schematic diagram, it is clear that liquid film is falling in the Y direction, whereas gas E is getting absorbed into the liquid in the Z direction. So at this point, you have Z is equal to 0, Y is equal to 0, whereas at the other end of the film, Z is equal to delta and Y is equal to 0. That means the thickness of the film is delta. The thickness of the liquid film is delta. Now at the top, where Y is 0 and Z is 0, Ca0 is the uniform concentration of E in the liquid. So at the top, Ce is equal to Ca0. And what is Ca0? Ca0 is the uniform concentration of E at Z is equal to 0 and y is equal to 0. At the liquid surface, we are talking about this liquid surface. At the liquid surface, CaI is the concentration of E that is dissolved in the liquid. So when E gets dissolved into the liquid, then on the surface, the concentration of E in the liquid is CaI. So on the surface, Ca is equal to CaI. Now this CaI, that is concentration of E in the liquid at the surface, it is in equilibrium with PaI. What is PaI? The pressure of E at the surface in the gas. So PaI, which is partial pressure of E in the gas, or not partial pressure, pressure of gas E at the surface. So it is this pressure, which I am denoting it as PaI. It is in equilibrium with CaI. What is CaI? CaI is concentration of E in the liquid at the surface. So we are talking about this point, the red dot that I have shown over here. Now what I am showing is the velocity profile. How the velocity in the y direction, it changes with z. So this is uy as a function of z. So as you move away from the surface, the velocity decreases, and when you are at the solid surface, velocity becomes 0. So this is velocity profile. So in this case, uy of z is the velocity of liquid in the y direction that changes in the z direction. It is changing in the z direction. Then at y is equal to L, this is how concentration of E in the liquid film or in the liquid it will change. So that is, it is changing as a function of z. So in this case, at y is equal to L, Ca of z is the concentration of E that changes in the z direction. Then we are going to consider an average concentration, which I will be denoting it as Cal bar. What is Cal bar? Cal bar is the average concentration of E in the liquid at y is equal to L. Even though Ca is changing with Z, in our discussion we are going to consider an average concentration, and that concentration we will be denoting by Cal bar. So in this case, at y is equal to L, Cal bar is the average concentration of E that is uniform throughout the liquid film. Ca bar is uniform throughout the liquid film, whereas Ca, it is changing with Z. How it changes, I have shown over here. So I hope you have understood the notations that I am using in my discussion. If you have any doubts, please mention them in the comment section. So what is the objective of the discussion? The objective is to get the mass transfer coefficient Ki that can be used to find the rate of absorption of gas E into the liquid as the liquid falls down through a distance L. So as the liquid is falling down in the y direction and it is in contact with gas E, and our objective is to get the mass transfer coefficient Kl, which we can use to find the rate of absorption of gas E into the liquid as the liquid falls down through a distance of L. So that is the objective. The objective is to get mass transfer coefficient. And what would be the approach? The approach is we are going to solve equation of continuity for component E and the equation of motion, that is Navier-Stokes equation. We are going to solve these two equations simultaneously in order to get the mass transfer coefficient. Now, in this discussion, we need to use many simplifying assumptions. Simplifying assumptions are required. Why? Because without these assumptions, we will not be able to solve the formidable set of partial differential equations. So, equation of continuity for E and then the equation of motion. These two form a formidable set of partial differential equations. And in order to solve them, we need to make some simplifying assumptions. Simplifying assumptions are required to solve these two equations. Let us move ahead. So now let us know those simplifying assumptions. What simplifying assumptions we will be using in the discussion? Let us first list those simplifying assumptions. First is there is no chemical reaction. First assumption. Second assumption is conditions do not change in the x direction. Let me tell you, we have shown the z direction, we have shown the y direction. X direction in this case is perpendicular to the plane. Perpendicular to the plane. So x direction is perpendicular to the plane. And what is the assumption? The assumption is we are going to assume that conditions are not going to change in the x direction. This is the second assumption. Then third assumption is steady state conditions are prevailing. Steady state conditions are prevailing. I will be discussing each of this assumption and what is the effect of that assumption on those two equations. I will be discussing it in details. Then fourth assumption is rate of absorption of gas is very small. I will talk more about it in my next day as I discuss how these simplifying assumptions are useful to us. For time being, you just know that the fourth assumption that we are going to make is the rate of absorption. Rate of absorption of gas E is very small. Then transfer of E by diffusion in the y direction, it is negligible as compared to the bulk transfer. So you know the liquid is moving in the y direction. So there is a bulk transfer of liquid. So as compared to this bulk transfer in the y direction, transfer of E by diffusion, it is negligible. And the fourth assumption is the rate of absorption of gas is very small. The meaning of this assumption is in the z direction, velocity in the z direction is very, very small. You can neglect it. So we will know more about it when we will be using it in our discussion. Then physical properties, they are constant. Physical properties like viscosity and then density, they are assumed to be constant. So these are the simplifying assumptions that we will be using in our discussion. Let us move ahead. Now let us first start with equation of continuity. So we will be using the equation of continuity for E. So I had derived it in my previous video. What is the equation? Dabba rho A by dabba T minus MA into DAB into dabba square CA by dabba X square plus dabba square CA by dabba Y square plus dabba square CA by dabba Z square plus UX into dabba rho A by dabba X plus UY into dabba rho A by dabba Y plus UZ into dabba rho A by dabba Z plus rho A into dabba UX by dabba X plus dabba UY by dabba Y plus dabba UZ by dabba Z, that is equal to RA into MA. I had derived this equation in my previous video lecture. Now the first assumption that we are using, there is no chemical reaction. And what is the implication of this assumption? RA is 0. So that means this term will become 0. So therefore now the equation of continuity modifies to this form. Dabba rho A by dabba T minus MA into DAB into dabba square CA by dabba X square plus dabba square CA by dabba Y square plus dabba square CA by dabba Z square plus UX into dabba rho A by dabba X plus UY into dabba rho A by dabba Y plus UZ into dabba rho A by dabba Z plus rho A into dabba UX by dabba X plus dabba UY by dabba Y plus dabba UZ by dabba Z, that is equal to 0. Why 0? Because there is no chemical reaction, therefore RA is 0, therefore RA into MA, it will be equal to 0. So this is how the first assumption modifies the equation of continuity for E. Let us move ahead. So we have the equation previously that was modified due to no chemical reaction. Now let us see what is the effect of second assumption. The second assumption is conditions do not change in the x direction. So what is the meaning of this assumption? The meaning is all derivatives with respect to x are 0. So therefore this equation will be modified to this form. Dabba rho a by dabba t minus ma into dab into dabba square ca by dabba y square. Now we have made this to be 0 because conditions are not changing in the x direction. So this is dabba square ca by dabba y square plus dabba square ca by dabba z square plus uy into dabba rho a by dabba y plus uz into dabba rho a by dabba z plus rho a into dabba uy by dabba y plus dabba uz by dabba z, that is equal to 0. So you must have noticed all derivatives with respect to x now we have omitted from the equation. So with the assumption of conditions not changing in the x direction, we get this equation. Let us move ahead. So previously we got this equation. Now let us see what is the effect of the third assumption. The third assumption is steady state conditions prevail. So the meaning of this is derivatives with respect to t, with respect to time, that will be 0. In this equation we just have one term and that will be 0. So therefore this equation will be modified to this form: minus ma into dab into dabba square ca by dabba y square plus dabba square ca by dabba z square plus uy into dabba rho a by dabba y plus uz into dabba rho a by dabba z plus rho a into dabba uy by dabba y plus dabba uz by dabba z, that is equal to 0. Let us move ahead. So previously we got this equation. Now let us look at the next assumption. The next assumption is rate of absorption of gas A is very small. So the meaning is uz velocity in the z direction, it is very small. uz is 0. So we will use that. So uz is in this term, so this term will become 0 and this term will become 0. So this equation modifies to this form: minus ma into dab into dabba square ca by dabba y square plus dabba square ca by dabba z square plus uy into dabba rho a by dabba y, and now this term has become 0 and this term has become 0, and so you are left with plus rho a into dabba uy by dabba y, that is equal to 0. Let us move ahead. So we got this equation. Now let us check with the other assumption. The other assumption is transfer of E by diffusion in the y direction. It is negligible as compared to the bulk transfer. So the diffusion term, which is this term dabba square ca by dabba y square, it will be 0 because in the y direction this is very small as compared to the bulk transfer. So with this assumption, and the equation will be modified to this form: minus ma into dab dabba square ca by dabba z square. Now dabba square ca by dabba y square, it has become 0, plus uy into dabba rho a by dabba y plus rho a into dabba uy by dabba y, that is equal to 0. Further, uy, it is changing in z direction. It is changing in the z direction, but in the y direction it is not changing. So therefore duy by dy, this term will become 0. So in that case, minus ma into dab dabba square ca by dabba z square plus uy into dabba rho a by dabba y, that is equal to 0. So with these two assumptions, we get this simplified form of the continuity equation for component E. Let us move ahead. So previously we got this equation: minus ma into dab dabba square ca by dabba z square plus uy into dabba rho a by dabba y is equal to 0. Now what I will do, I will divide this equation with ma, the molecular weight of E. So it will be ma upon ma, it will get cancelled. So we are left with minus dab into dabba square ca by dabba z square plus uy into, I will divide with ma and take it into the differential. So it will be dabba rho a by ma by dabba y, that is equal to 0. But we know that rho a upon ma is nothing but ca. So it will, the equation will be minus dab dabba square ca by dabba z square plus uy into dabba ca by dabba y is equal to 0. Or I can write it like this: uy into dabba ca by dabba y, that is equal to dab into dabba square ca by dabba z square, and I am going to call this as equation number 1. So equation number 1 is the modified form of equation of continuity for E. And why it is modified? Because we have made many simplifying assumptions. So we are left with the equation number 1. Uy into dabba Ca by dabba y, that is equal to dab into dabba square Ca by dabba z square. I am calling this as equation number 1. Let us move ahead. Now that completes our analysis for the equation of continuity for E. Now let us do the analysis for equation of motion. So equation of motion, in this case bulk flow is in the y direction, and that's why as the liquid film is flowing in the y direction, only y component of the equation of motion is we are going to consider. And what is that y component? It is given like this: rho into dabba uy by dabba t plus ux into dabba uy by dabba x plus uy into dabba uy by dabba y plus uz into dabba uy by dabba z, that is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba x square plus dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. So this is the y component of equation of motion. And why we are just considering the y component? Because in this case flow is in the y direction. Let us continue with this. Now we are going to check what will be the implications of assumptions on this equation. So let us move ahead. So we have the equation of motion: rho into dabba uy by dabba t plus ux into dabba uy by dabba x plus uy into dabba uy by dabba y plus uz into dabba uy by dabba z, that is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba x square plus dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. Now the assumption, which assumption? Conditions do not change in the x direction. So what is the implication of this assumption? All derivatives with respect to x will be 0. So this will be 0 and then this will be 0. So the equation will be modified to this form: rho into dabba uy by dabba t plus uy into dabba uy by dabba y plus uz into dabba uy by dabba z, that is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. Let us continue with this. So we got this equation with the first assumption. After using the first assumption, now let us check with the other assumption. What is the other assumption? The other assumption is the steady state conditions prevail. That means derivative with respect to time, they will be 0. There is one term, so this will become 0. So it will be rho into dabba rho into uy into dabba uy by dabba y plus uz into dabba uy by dabba z, that is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. So you must have noticed I have directly taken the equation y component of equation of motion in my discussion. I will make a separate video on how to derive equation of motion. But for time being in this discussion, I have directly taken the equation of motion in my discussion. And as we need just the y component, we have considered the y component of equation of motion. Let us move ahead. So we have this equation: rho into uy into dabba uy by dabba y plus uz into dabba uy by dabba z, that is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. Now let us check with the other assumption. The other assumption is rate of absorption of gas E is very small. That is velocity in the z direction, it is 0. So this term will become 0. So it will be rho into uy into dabba uy by dabba y. This is 0. That is equal to minus dabba p by dabba y plus mu into dabba square uy by dabba y square plus dabba square uy by dabba z square plus rho into g. Further, uy changes only in the z direction. So dabba uy by dabba y, it will become 0. Dabba square uy by dabba y square, it will also become 0. and p is also constant. So therefore dabba p by dabba y, that will also become 0. So we are left with 0. This is 0 because dabba uy by dabba y is 0. So 0 is equal to mu into dabba square uy by dabba z square plus rho into g. That is mu into dabba square uy by dabba z square plus rho into g is equal to 0. And I am going to call this as equation number 2. So equation number 2 is the modified form of y component of equation of motion. And how we have modified it? We have modified it by using the simplifying assumptions in our discussion. Let us move on. So we have equation 2, mu into dabba square uy by dabba z square plus rho into g is equal to 0. Now let us integrate this equation. So it will be integration of mu dabba square uy by dabba z square dz plus integration of rho g dz, that is equal to c1. c1 in this case is the constant of integration. Now over here mu, rho and g, they are constant and they will come out of the integral. So it will be mu into integration of dabba square uy by dabba z square into dz plus rho into g into integration dz, that is equal to c1. c1 is the constant of integration. Let us continue with this. So we got this mu into integration dabba square uy by dabba z square dz plus rho into g into integration dz, that is equal to c1. So integration of dabba square uy by dabba z square is dabba uy by dabba z. So mu into dabba uy by dabba z plus integration of dz is z. So it is plus rho g into z, that is equal to c1, and I am going to call this as equation number 3. And again I will integrate equation number 3. So it will be integration of mu dabba uy by dabba z into dz plus integration of rho g z dz, that is equal to integration of c1 dz plus c2. And again c2 in this case is the constant of integration. Let us continue. So we have this equation, integration of mu dabba uy by dabba z dz plus integration rho g z dz, that is equal to integration c1 dz plus c2, where c2 is the other constant of integration. Now in this case mu, rho and g, these are constant, so they will come out of the integral. So it will be mu integration of dabba uy by dabba z dz plus rho into g integration z dz, that is equal to c1 integration dz plus c2, the constant of integration. So it will be mu into uy plus rho g integration of z dz is z square by 2. So it is rho g z square by 2, that is equal to c1 z plus c2. And now I am going to call this as equation number 4. Now we will be in order to get the constant c1 and c2, we will be using these boundary conditions. So at z is equal to 0, that is at the interface between liquid and gas, at z is equal to 0, dabba uy by dabba z, this differential is 0. Whereas the other condition is at z is equal to delta, that is at the wall, velocity is 0. So at z is equal to delta, uy is equal to 0. So by using these two boundary conditions, we are going to get the constants of integration, that is c1 and c2. Let us move ahead. Okay, so first we will use equation number 3 to get constant c1. So what was equation 3? Mu into dabba uy by dabba z plus rho g z, that is equal to c1. And the first boundary condition is at z is equal to 0, dabba uy by dabba z is 0. So if we use this boundary condition in this equation, it will be mu into 0, dabba uy by dabba z is 0, plus rho into g at z is equal to 0. So it is rho into g into 0, that is equal to c1. So that gives us c1 as 0. Now let us use equation number 4 to get the other constant c2. So it would be, what is equation 4? Mu into uy plus rho into g z square by 2, that is equal to C1z plus C2. So we are going to use equation number 4 to get the other constant. First constant, that is C1, is 0. We have already found out. Let us move ahead. So we have equation 4, mu into uy plus rho g z square by 2, that is equal to C1z plus C2. C1 is 0. So therefore the equation will be mu into uy plus rho g z square by 2, that is equal to 0 into z plus C2. That is mu into uy plus rho g z square by 2 is equal to C2. Now once you get this equation, we will use the other boundary condition. What is that? At z is equal to delta, mu uy is 0. So it will be mu into 0 plus rho into g into delta square by 2, that is equal to C2. So we have replaced z with delta and uy with 0, and we are getting this equation. Let us move ahead. So we have mu into 0 plus rho g delta square by 2 is equal to C2. So this is 0. So it will be 0 plus rho g delta square by 2 is equal to C2. That is C2 is rho g delta square by 2. So if you use the values for constant C1 and C2 that we have obtained in equation number 4, which is the equation 4 is mu into uy plus rho g into z square by 2, that is equal to C1z plus C2. Now we are going to use the constants that we have obtained. C2 is rho g delta square by 2, whereas C1 is 0. So in the next step we will be putting those constants in this equation. So let us move ahead. So we have mu uy plus rho g z square by 2, that is equal to C1z plus C2. C1 is 0. C2 is rho g delta square by 2. So it will be mu uy plus rho g z square by 2, that is equal to C1 is 0. So 0 into z plus C2 is rho g delta square by 2. So that is mu uy plus rho g z square by 2, that is equal to rho g delta square by 2. We will continue with this in the next step. So we have mu uy plus rho g z square by 2, that is equal to rho g delta square by 2. So that is mu uy is equal to rho g delta square by 2 minus rho g z square by 2. So this term is brought on this side. So in the next step we can take rho g common. So it will be mu uy, that is equal to rho g delta square by 2 into 1 minus z square by delta square. So here what is done? Rho g delta square is taken common. Rho g delta square by 2, it is taken out as a common term. So that's why you have rho g delta square by 2 into 1 minus z square by delta square. So that is uy is equal to rho g delta square upon 2 mu into 1 minus z square by delta square. And I am calling this as equation number 5. Now let me tell you what are the terms involved in this equation. So in the beginning I didn't tell you what are the terms involved. So after getting equation 5, in equation 5 uy is the local velocity, uy, which is function of z. So as you move on along the liquid film, uy is changing. So uy is changing locally. So that's why it is local velocity. So uy is the local velocity that changes with z, that is uy as a function of z. Then rho in this equation is density, g is acceleration due to gravity, delta is the thickness of the film, mu is viscosity of the liquid, and z is the distance from the surface. As you move away from the surface towards the wall, z is going to increase. So we get equation number 5. Equation number 5 gives you local velocity as a function of z. So this uy is going to change with z. So I hope equation number 5 is clear to you. Let us move ahead. But instead of using local velocity, we need the bulk average velocity for the liquid film. The bulk average velocity with which the liquid is falling down. We need to know that. So for that we will consider a problem of an inclined plate. So let us consider a plate that is making an angle of theta with the vertical, and if a liquid is flowing on this plate in the form of a thin film, then for this problem the bulk average velocity, it is given by this equation. Uy bar is equal to rho g delta square cos of theta by 3 mu. So you can derive this equation, but in my discussion I am directly taking the equations into my discussion. So for a problem of an inclined plate on which a liquid is falling down or liquid is coming down in the form of a thin film, and if the plate is making an angle of theta with the vertical, then the bulk average velocity for the liquid is given by this equation. U bar y is equal to rho g delta square cos of theta by 3 mu. Now for our problem, which is a vertical wall, in our problem we have a vertical surface, and when this surface becomes vertical, theta is 0. So in our case, the bulk average velocity u bar y will be equal to rho g delta square cos of 0 by 3 mu. That is u bar y will be equal to rho g delta square by 3 mu, because cos of 0 is 1. So bulk average velocity for our problem, or the bulk average velocity with which the liquid is falling down, it is given by this equation. U bar y is equal to rho g delta square upon 3 mu. Let us move ahead. So we got an equation for the bulk average velocity, which is u bar y is equal to rho g delta square by 3 mu. So if we use it in equation number 5, which is uy is equal to rho g delta square by 2 mu into 1 minus z square by delta square, which gives us the local velocity. Now if this is rearranged, so if I do this rearrangement, uy is equal to, I am multiplying with 3 and dividing with 3, so it will be uy is equal to 3 upon 3 into rho g delta square upon 2 mu into 1 minus z square by delta square. So that is uy is equal to 3 by 2. Now I am bringing 2 at this position and taking this 3 to this position. So it will be uy is equal to 3 by 2 into rho g delta square by 3 mu into 1 minus z square by delta square. And rho g delta square by 3 mu is nothing but u bar y. So therefore uy will be equal to 3 by 2 uy bar into 1 minus z square by delta square. Now I am calling it as equation number 6. Let us move on. Now let us solve the two equations simultaneously. The equation of continuity for E and then the equation of motion. So the continuity equation for E, we got it earlier. Uy into dabba Ca by dabba y is equal to dab into dabba square Ca by dabba z square. That was equation number 1. And we just got equation of motion. Equation of motion gave this resulted in this equation. Uy is equal to 3 by 2 u bar y into 1 minus z square by delta square. That was equation number 6. Now if we use equation 6 in equation 1, that is, we will be replacing uy in equation number 1. So it will be 3 by 2 u bar y into 1 minus z square by delta square into dabba Ca by dabba y, that is equal to dab into dabba square Ca by dabba z square. So what have I done? I have replaced uy in equation number 1. So let us move ahead. So we have 3 by 2 uy bar into 1 minus z square by delta square into dabba Ca by dabba y, that is equal to dab into dabba square Ca by dabba z square. I am going to call this as equation number 7. Now equation number 7, we need to solve it, and for that we will need limits because it is a differential equation. So equation number 7, it can be solved with these limits. At z is equal to 0, that is at the interface between liquid and gas, at every point for all values of y, Ca is CEI. That means at all the points on the interface, Ca is CEI. Then the second condition is at z is equal to delta, that is at the boundary, dabba Ca by dabba Z is 0. So at the wall, the differential dabba Ca by dabba Z is 0, and this is true for all values of y. It is true for the entire length of the vertical surface. Then the third condition is at y is equal to 0, Ca is Ca naught. So when you are at this point, that is at y is equal to 0, Ca is Ca naught everywhere, for all z's. So when you use these three boundary conditions to solve equation number 7, I am not going to solve it over here. I will tell you what would be the nature of the solution. So if you solve equation number 7 with these boundary conditions, the solution will give us a general expression which is an infinite series. So the solution will give us an infinite series. And what is the peculiarity of this infinite series? This infinite series, or this general expression, it gives Ca as a function of z and y. So the equation will tell you how Ca is changing with z and y. So the point is, if you solve equation number 7, which was obtained by combining the continuity equation for A and the equation of motion, if you solve equation number 7 with these boundary conditions, you are going to get a general expression, which is nothing but an infinite series. And this expression will tell you how Ca is changing with z and y. How Ca changes with z and y. So I hope this is clear to you. I hope I hope you have understood what I mean by simultaneous solution of the continuity equation and then the equation of motion. So let us move. Then we will also know how you can calculate the thickness of the film, because when you have a problem based on this, you will need to calculate the thickness. So let us understand how you can get the thickness of the film. So for that, we will be using the equation for bulk average velocity. What is the equation? Uy bar is equal to rho g delta square by 3 mu. That is 3 mu uy bar by rho g is equal to delta square after rearranging it. So that gives us delta as 3 mu uy bar by rho g raised to 1 by 2. So you can use, if uy bar is known to you, you can use this equation to get the thickness of the film. But you can also have an equation for delta in terms of mass flow rate. Mass flow rate per unit width of the film. And how it is given? If we denote mass flow rate per unit width of the film by m, so it will be given by this equation: bulk average velocity into density into flow area. So m will be, bulk average velocity is u bar y, uy bar, just a minute. So this is uy bar, the bulk average velocity, into density into the flow area. Flow area is the area which is obtained by multiplying the thickness with width in the x direction, and we have considered the width to be unity. The unit is the width is considered to be 1. So the flow area will be delta into 1. So this is delta, and perpendicular to this plane will be the width, and we are assuming it to be 1. So the flow area will be delta into 1 in the perpendicular direction. So therefore, equation for m is uy bar into rho into delta into 1. Let us continue with this. So we have m is equal to uy bar into rho into delta into 1, and that is now we can replace, we know we have equation for uy bar. So uy bar is rho g delta square by 3 mu. So we will use this equation over here. So it will be m is equal to rho g delta square by 3 mu. We have replaced this, rho g delta square by 3 mu into rho into delta into 1. That is 3 mu into m is equal to rho square, rho into rho square g delta square into delta is delta q. So that is 3 mu into m by rho square g is delta q. that is delta is equal to 3 mu young by rho square g raised to 1 by 3. So most of the time mass flow rate per unit width will be known to you. So if that is the case, then you can use this equation to get the thickness of the film. Let us move ahead. Now after getting the thickness, the next task is to get the mass transfer coefficient. How to get mass transfer coefficient in this laminar flow? Let us understand. Now the rate of absorption of A into the liquid over a distance is equal to the rate at which A is carried by the film over that distance. You need to understand this fact. Rate of absorption of A into the liquid over a distance. So as a liquid moves over some distance, then the rate at which A is absorbed into the liquid, this rate is equal to the rate at which A is carried by the film over that distance. So as A gets absorbed into the liquid and liquid moves through a certain distance, so the rate of absorption is equal to the rate at which A is carried by this liquid over that distance. So we are going to use this fact to get the equation for mass transfer coefficient. The rate of absorption of A into the liquid as it moves over a distance is equal to the rate at which A is carried by the film over that distance. I hope this is clear to you. If you have any doubt, you please mention that in the comment section. So now let us first get rate of absorption of A over some distance, and let that distance be dy, differential distance. So let us get rate of absorption of A over a distance dy. And we are going to get that rate per unit width of the film in the x direction, which is perpendicular to this plane. So per unit width of the film in the x direction. So the rate will be RAA. I am going to denote that rate as RAA. So RAA will be equal to NAA into area for mass transfer. That is the flux, mass transfer flux, which will be moles per unit time per unit area. And if I multiply with area, so it will be moles per unit time. So RAA will be equal to NAA, the mass transfer flux, into area through which this mass transfer occurs. So therefore RAA will be equal to NAA, and the area through which this mass transfer occurs, it will be the vertical distance in the y direction and unit distance in this x direction, because we are assuming to be unit width in the x direction. So that is why RAA, which is rate of absorption in moles per unit time, is equal to mass transfer flux in moles per unit time per unit area into area for mass transfer, and area for mass transfer over this distance, over the differential distance dy, is dy into 1. 1 is the dimension in the x direction, which is perpendicular to this plane, and I am going to call this as equation number 8. So we have this equation, rate of absorption. We have equation for the rate of absorption of A over a distance dy. The equation was RAA is equal to NAA into dy into 1. That was equation number 8. Now NAA, we are going to express it in terms of mass transfer coefficient. How? NAA will be equal to mass transfer coefficient into driving force. So that is NAA will be equal to the mass transfer coefficient is KL, and the driving force is difference between the concentration at the surface and the average concentration within the liquid. So the equation is NAA is equal to KL into CAI minus CA bar, where CA bar is the average concentration at any Y in the liquid. KL is the mass transfer coefficient, as I said, and CAI is the concentration at the interface, that is surface, liquid surface, and CA bar is the average concentration E in the liquid. So we have an equation for NAA. So the task would be, we will be using this equation in equation number 8. So therefore equation number 8 will become RAA is equal to KL into CAI minus CA bar into dy into 1, and let us call this as equation number 9. So let us continue with this. So after getting equation for rate of absorption over a distance dy, now let us get an equation for rate at which A is carried over the same distance. Which distance? Dy. Rate of carrying of A over a distance dy. So again it will be expressed per unit width of the film in the x direction perpendicular to the plane. So the concentration change in this case, so as A is carried over a distance dy, the concentration change over this distance would be dCA. Let that concentration be dCA, a differential change in the concentration. So the rate at which A is carried over a distance dy, I am denoting it as RCA. So RCA will be equal to bulk average velocity into area for flow into change in concentration. So that is RCA will be equal to U bar Y, Ui bar, the bulk average velocity, into the flow area is delta into 1. So delta into 1 in the perpendicular direction, in the x direction. So that will be the flow area. So Uy bar, the bulk average velocity, delta into 1 is the flow area, and change in concentration, the differential change in concentration is dCA bar, and I am calling this as equation number 10. So we have RAA, we got it earlier, KL into CAI minus CA bar into dy into 1, that was equation number 9, and we just got RCA is equal to Uy bar into delta into 1 into dCA bar, that was equation number 10. So but the condition is RAA, rate of absorption is equal to rate at which it is carried away over the same distance. So RAA is equal to RCA, that is KL into CAI minus CA bar into dy into 1 is equal to Uy bar into delta into 1 into dCA bar. So RAA is equal to RCA. We are using equations for each of the two, and then we get this. So it will be KL into CAI minus CA bar into dy on this side, and on the other side it will be Uy bar into delta into dCA bar. Let us continue with this. So we have KL into CAI minus CA bar dy, that is equal to Uy bar into delta into dCA bar. Let me just show Uy bar and dCA bar. Let us continue with this. So KL into dy is nothing but is equal to Uy bar into delta into dCA bar by CA minus CA bar, and this is equation number 11. Equation number 11 is a differential equation. So it is a differential equation, and you can solve. We need to solve it, and for solving that differential differential equation, what are the limits available at y is equal to 0? So when you are at this, CA bar is nothing but the initial concentration CA naught, and then at y is equal to L, when you are at this point, CA bar is nothing but the average concentration at y is equal to N. And what is that? That is CAL bar. So let us solve equation number 11 with these boundary conditions. Let us move on. So we have equation 11, we got it earlier. KL into dy is equal to Uy bar into delta into dCA bar by CAI minus CA bar. At is y is equal to 0, CA bar is CA naught, and at y is equal to L, CA bar is CAL bar. So it will be integration from 0 to L, KL dy, that is equal to integration from CA naught to CAL bar into Uy bar delta into dCA bar by CAI minus CA bar. Let us continue with this. So we have integration from 0 to L KL dy, that is equal to integration from CA naught to CAL bar into uy, integration of uy bar into delta into dCA bar by CAI minus CA bar. Now what are the constants in this case? Uy bar is constant, the bulk average velocity is constant, delta is constant, the thickness of the film, and in the case of mass transfer coefficient, an average value of KL, which we will be denoting by KL average, it is considered to be constant for the entire gas liquid interface. So KL average will be KL will be replaced with KL average, and then it being constant, it will be coming out of the integral. So let us move ahead. So we have integration from 0 to L KL dy, that is equal to integration from CA naught to CAL bar uy bar delta dCA bar by CAI minus CA bar. Now KL will be replaced with KL average. So integration 0 to L KL average dy, that is equal to integration from CA naught to CAL bar uy bar delta dCA bar by CAI minus CA bar. So KL average will come out of the integral. So it is KL average into integration from 0 to L dy, that is equal to uy bar delta. Both are constant, so they have come out of the integral. Uy bar delta into integration from CA naught to CAL bar dCA bar by CAI minus CA bar. Let us continue with this. So we have KL average into integration 0 to L dy, that is equal to uy bar delta into integration CA naught to CAL bar into dCA bar by CAI minus CA bar. Now let us integrate it. So it will be KL average, integration of dy is y. So y limits are 0 to L, that is equal to uy bar into delta integration of dCA bar by CAI minus CA bar. It is ln of CAI minus CA bar divided by coefficient of CA bar, and the coefficient is -1. So it is ln of CAI minus CA bar upon -1, and limits are CA naught to CAL bar. So that is KL average is into y, limits 0 to L, that is equal to uy bar into delta, and now I will absorb this negative sign. For that I will have to interchange the limits. So it will be KL average y limits 0 to L, that is equal to uy bar delta into ln of CAI minus CA bar, and now limits are CAL bar to CA naught. So this is CAL bar. So let us use the limit. So it is KL average L minus 0, that is equal to uy bar delta into ln of CAI minus CA naught minus ln of CAI minus CAL bar. So this is uy bar, this is CAI minus CA naught minus ln of CAI minus CAL bar. Let us continue with this. So we have KL average into L minus 0, that is equal to uy bar into delta into ln of CAI minus CA naught minus ln of CAI minus CAL bar. So in the next step, it will be KL average into L, and this is I have used the logarithmic identity. Ln of m minus ln of n is ln of m upon n. So that's why you get this KL average into L is equal to u bar y into delta into ln of CAI minus CA naught divided by CAI minus CAL bar. So that is KL average is equal to uy bar into delta by L into ln of CAI minus CA naught divided by CAI minus CAL bar. So we get an equation for KL average, and this equation is nothing but the defining equation for the average mass transfer coefficient. The average mass transfer coefficient is KL average. Let us continue with this. So we got an equation for KL average. It is uy bar delta by L into ln of CAI minus CA naught by CAI minus CAL bar. So in order to use this equation to get KL average, so this equation can be used if CAI and CAL bar, these are known to us. So this is one way you can use it, but if you have to use it, the problem is CAI and CAL bar, they should be known to us. We also have some other equations that have been proposed. Equation for finding KL average. So KL average can be approximately found out by using those equations. So we will know what are these equations. So KL average can be approximately found by using other equations. Now what are these other equations? Let us know. So for small rates of flow or for long contact times between gas and liquid. So if the flow rate is small, and the other case is if there is a long contact between liquid and gas, then the film Reynolds number will be less than 100 for this case, for small rates of flow or for long times of contact between gas and liquid. So the film Reynolds number is less than 100. So the film Reynolds number is given by this equation, 4m by mu, and it is less than 100 for this case. So m is in this case is the mass flow rate, and mu is the viscosity, mass flow rate per unit weight, and mu is the viscosity. So if that is the case, then you can calculate KL average by using this equation. KL average will be equal to 3.41 into DAB by delta. Then for high rates of flow or for short times of contact between gas and liquid, the Reynolds number will be higher. It will be greater than 100 when the film Reynolds number is greater than 100. That is RE, which is calculated as 4m by mu. It is more than 100. M is the mass flow rate, mu is the viscosity. We know that. So in that case, KL average will be calculated by using this equation. KL average is equal to 6 DAB into m by pi into rho into delta into L raised to 1 by 2. So depending on the film Reynolds number, you have the equation for calculating KL average. So you can use these equations for finding the average mass transfer coefficients. And we will know how to use these equations. In my next video lecture, I will be discussing one numerical where we will estimate mass transfer coefficients in laminar flow. So there we will learn how to use these equations. Equation for KL average when RE is less than 100 and when it is greater than 100. So let us move on. Okay, now next we will find the total absorption rate. The total absorption rate for the entire gas liquid surface. So we are interested in finding out the rate of absorption that is taking place along the entire gas liquid surface. So it will be given by this equation. RA average is equal to bulk average velocity into flow area into change in concentration. So this equation will give a rate in moles per unit time. Bulk average velocity into flow area into change in concentration. So that is RA average is equal to U y bar is the bulk average velocity, delta into 1 is the flow area, the area through which flow is occurring, thickness into 1, why 1? Because we have considered unit width in the x direction, and x direction is perpendicular to the plane. So therefore RA average is uy bar into delta into 1, and the change in concentration that occurs across the entire gas liquid surface. So when you are at the top, the concentration is CA0, and when you reach at y is equal to L, you have the average concentration CAL bar. So that's why change in concentration is CAL bar minus CA0. CAL bar minus CA0. So that is RA average is equal to U bar Y into delta into CAL bar minus CA0. Okay, now if you have to express rate as the mass transfer flux, we will have to express it in terms of the mass transfer coefficient KL average. So we have the equation RA average U bar by into delta into CAL bar minus CA naught U y bar and CAL bar. So RA average is the rate, absorption rate in moles per unit time. If you have to express it as mass transfer flux, the mass transfer flux, let us denote it as NA average. It will be obtained by dividing RA average with the area for mass transfer. So moles per unit time divided by area will give us the mass transfer flux. So rate now is expressed as mass transfer flux, and it will be expressed in terms of the mass transfer coefficient. So NA average is equal to RA average is UY bar into delta into CAL bar minus CA naught divided by area for mass transfer is L into 1. So mass transfer is taking place along the entire surface, whose length is L and width is 1. Width is 1 in the x direction. So therefore area for mass transfer is L into 1. So L into 1, which is perpendicular to the plane. So that will give us NA average. So NA average is UR by into delta into CAL bar minus CA naught by L. So NA average, one thing is you can find out by using this equation, but we will express NA average in terms of the mass transfer coefficient, because we will be learning how to use, the mass transfer coefficient to find the absorption rate. So let us continue with this. So at the end of this particular discussion, we have one equation for NA average, the mass transfer flux, which will give the absorption rate in moles per unit time per unit area. Let us continue with this. Okay, so we have this equation. NA average is equal to U y bar into delta into CAL bar minus CA naught by L. Now we will try to bring the average mass transfer coefficient in this equation. So basically we want to express this equation in this form. NA average is equal to the mass transfer coefficient KL average into concentration difference delta C E. The concentration difference is CAL bar minus CA naught. So we want to have the mass transfer coefficient in this equation. So for that, what I will do, I will multiply and divide this equation with a logarithmic term that is there in the definition of KL average, if you remember the equation for KL average. So what I am doing, NA average is equal to UY bar into delta into CAL bar minus CA naught divided by L. Now I am multiplying with ln of CAI minus CA naught by CAI minus CAL bar, and at the same time I am dividing with ln of CAI minus CA naught divided by CAI minus CAL bar. So I am taking this logarithmic term into the equation because we have the term in the definition of the average mass transfer coefficient, if you remember. So it will be NA average is equal to, I will write it in a proper form. So NA average is equal to UY bar into delta by L into ln of CAI minus CA naught divided by CAI minus CAL bar. And then you have the concentration difference CAL bar minus CA naught divided by ln of CAI minus CA naught divided by CAI minus CAL bar. I have just rearranged it so that I'm getting this group. I'm getting this group in the equation, and this group is nothing but the definition for the average mass transfer coefficient. So let us continue with this. So we just got this equation. NA average is equal to UY bar into delta by L into ln of CAI minus CA naught divided by CAI minus CAL bar into CAL bar minus CA naught divided by ln of CAI minus CA naught divided by CAI minus CAL bar. But this group is the average mass transfer coefficient. Which group? This group is the average mass transfer coefficient. So that's why you get this equation. NA average is equal to KL average. This is the term in this bracket is KL average into CAL bar minus CA naught divided by ln of CAI minus CA naught divided by CAI minus CAL bar. Let us continue with this. We will rearrange this equation. So we got this NA average is equal to KL average into CAL bar minus CA naught divided by ln of CAI minus CA naught divided by CAI minus CAL bar. Now what I will do in this term in the numerator, I will add CAI and at the same time I will subtract CAI, so that I can get these two terms CAI minus CA naught and CAI minus CAL bar over here. So NA average is equal to KL average is KL average into CAL bar minus CA naught plus CAI minus CAI. I have added CAI and at the same time I have subtracted CAI divided by ln of CAI minus CA naught divided by CAI minus CAL bar. Now this term in the numerator, it can be written in a different form. So NA average is equal to KL average into CAI minus CA naught. So CAI minus CA naught, and then if I take minus common in the bracket, it will be CAI minus CAL bar. So if you just multiply with the negative sign in this bracket, it will be minus CAI plus CAL bar, which will give this result. So you are getting NA average is equal to KL average into CAI minus CA naught minus CAI minus CAL bar divided by CAI minus CA naught divided by CAI minus CAL bar. So in the numerator you have one term minus the other term, and in the denominator you have log ln of the first term divided by the second term. So this is the logarithmic average of these two brackets, CAI minus CA naught and CAI minus CAL bar. Let us move ahead. So we have NA average is equal to KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. So now I can write this equation in this form. NA average is equal to KL average into CAI minus CA bar m, where CAI minus CA bar m is this term, the logarithmic average. So this term is the logarithmic average of this term and this term, and I am denoting that logarithmic average by CAI minus CA bar m. So in this case, CAI minus CA bar m is CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. So now we have got an equation where you have the mass transfer flux, the mass transfer coefficient, and the concentration difference, which is the logarithmic average of the two terms, these two terms. So I hope the steps that I have used in getting this equation, those steps are clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Okay, so based on all the discussion that we have done so far, based on the equations that we have got, now let me summarize what calculations are involved in dealing with a problem of finding mass transfer coefficients in laminar flow. So what calculations are involved? Let me summarize. First, you will have to find thickness of the film. So for that you can use this equation. Delta is equal to 3 mu into m by rho square into g raised to 1 by 3. Then you can find bulk average velocity. For that you can use this equation. Uy bar is equal to rho g delta square by 3 mu. We got this equation earlier. Then you can find film Reynolds number by using this equation. Re is equal to 4m by mu. Let us continue with this. Then after getting the film Reynolds number, we have to get the average mass transfer coefficient, because the equation that we have to use for finding the average mass transfer coefficient, it depends on the film Reynolds number. So if the film Reynolds number is less than 100, then you can find KL average by using this equation. KL average is equal to 3.41 into DAB upon delta. And if the film Reynolds number is greater than 100, then you can find KL average by using this equation. C is 6 DAB into M by pi rho delta, pi into rho into delta into L raised to 1 by 2. So in this way, you can find, you have to use the equation depending on the Reynolds number. If it is less than 100, you have to use this equation. If it is greater than 100, then you have to use this equation. Let us move ahead. Next, you have to get the average concentration, that is CAL bar. And for that, we will be using equation for NA average. So NA average is either KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. And at the same time, NA average is also UY bar into delta into CAL bar minus CA naught by L. So that is KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught by CAI minus CAL bar is equal to UY bar into delta into CAL bar minus CA naught by L. So you have this equation in which CAL bar is the unknown. So you just have to solve this equation for getting CAL bar. So in this way you can find the average concentration CAL bar. Let us continue with this. And after getting CAL bar, then you can find the total absorption rate. So if you have to get it in moles per unit time, you can use this equation. RA average is equal to UY bar into delta into CAL bar minus CA naught. And if you have to get it as mass transfer flux, moles per unit time per unit area, then you can use this equation. NA average is equal to UY bar into delta into CAL bar minus CA naught by L. Or you can also use this equation, which is in terms of KL average. So NA average is equal to KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught by CAI minus CAL bar. So in this way, you can find the total absorption rate. So with this, I will end my discussion for estimation of mass transfer coefficients in laminar flow. So at the end, I have told what steps are involved in the calculations. So whenever you have a numerical based on this, you can follow those steps. In order to make these steps more clear to you, I will be discussing a numerical based on this particular concept in my next video lecture. For now, I will end the discussion for this video lecture. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and hope to see you soon in my next video lecture. Thank you. Bye bye.